Alright, clowns. So we're gonna get started in a little bit. I am just gonna wait on a few people to join. So let's wait maybe a couple of minutes and then we can get started. Before that, if there's any questions that you have, I'd like to start by going over the homework. That'd probably be a good idea, right? Imagine me having good ideas. Um, Alright. So yeah, we're gonna start with the homework, and if people have questions, they can feel free to ask. And then at the end of that, we can go through some stuff. Yeah, no, I'm alive. I promise. I just have some other stuff to do. Where's the professional dress at? That's only for Thursday. You should know this at this point. Okay. So question number one. And remember, all these questions are based on this information right here. That Q1 has a charge of 2 times 10 to the negative 6 coulombs. And Q2 has a charge of negative 4 times 10 to the negative 6 coulombs. So the magnitude of the electrostatic force on Q1 due to Q2 is 1.8 newtons. What is the magnitude of the electrostatic force on Q2 due to Q1? It is the same kind of question as anything to do with like, oh, you're pushing a horse. The horse pushes you back, and you're pushing it with a force of 40 newtons. What force is the horse pushing you back with? Oh, no audio. Okay, hold on. Huh, that's fine. Can y'all hear me now? Hopefully. Yes, no? You should be able to hear me. Huh. Okay, cool. So this first question is really just the same idea as any other force question. Equal and opposite forces. I can try to turn up my mic, but I don't know what difference it's going to make. Nothing's really changed from yesterday. Okay. So we have, like, when we apply a force on something, right? So let's say that you're pushing on another person, and you're pushing on that other person with a force of 40 newtons. That person is going to push you back with a force of 40 newtons. That's Newton's third law, equal and opposite forces. Newton's third law still holds for electrostatic forces. So question one, if the force on Q1 due to Q2 is 1.8 newtons, the force on Q2 to Q1 is the same idea. It's still 1.8 newtons. It should be equal values. So here the answer to number one was D. I'm not entirely sure how I can edit this PDF. I guess I can do that. Cool. Number two, the charges would feel a force that is. Okay, so we've got a negative 2 times 10 to the negative 6 coulomb charge here, and a negative 4 times 10 to the negative 6 coulomb charge here. Negative and a negative should be repulsive. That is my answer for number two. Number three, the electric field between the two charges. So this is still talking about these two charges up here. Now, important thing to keep in mind. It's two negative charges, and remember that when we draw in electric field lines, we have to draw them in with the assumption that we're thinking about how small positive test charges would interact with these charges. So like every single arrow that you see is like a small positive test charge, and we think about how those would interact with my other charges. So we have two negative charges drawn here. It can't be A because that's not two negative charges. It can be either B, C, or D. And I know that for my drawings to be done correctly, I need to point arrows towards the negative charge. Because those small positive test charges that surround my negative charges are going to be attracted to the negative charges. Now, C and D are incorrect because we know that negative charges would never interact like this. They would never be pulled towards each other like this. And those small positive test charges would not be rejected by this negative charge and attracted by only this one. They have to be attracted by both, and so that's going to give us the answer choice B. I don't know how to highlight this. I don't think I can. That's unfortunate. Okay, well, that's going to be as good as it's going to get. Okay, so two metallic spheres, A and B, are separated by a distance of 0.5 meters as shown. The charge on sphere A is plus 9 times 10 to the negative 6 coulombs, and on B is 1.6 times 10 to the negative 6 coulombs. What is the magnitude of the electric force between the two charged spheres? So this is going to be, I'm actually going to change it up here so we can do some of the math. So this is going to be using the same formula that we always use when we are given two different objects and we are asked for electric force, and that is F is equal to K. Can you say a bad word? No. A K Q1 Q2 over R squared. We start to fill in information, so you know that the distance, the R is 0.5, Q1 is plus 9, Q2 is negative 1.6, and K is your constant, which is 8.99 E9. When you solve this out, I believe that you get answer choice B. So B is the correct answer here. Cool. Questions, Rokia. You put A for 3. So do you want to go over 3 again? Or are you a little confused? Also, how do I take it off this setting? Oh, well, that's a rip. That's going to have to be the setting for the rest of this day. Is it for completion or accuracy? I haven't decided yet. I'll figure it out around 12. Number 5, the excess is produced by which elementary particles? So, if we have an excess charge of 9.6 times 10 to the negative 19th, that is a positive value. That is not a negative value. That is a positive value. So, it's going to be protons. Answer choice B. And finally, for number 6, the real problem is that the right answer was not written in here, which kind of sucks. I corrected it. If you did it off of the second period group chat or Google Classroom, then it should be corrected. But yeah, it wasn't corrected when you first got it. So the equation provided in the puzzle video is the equation that I gave in the stream yesterday, which was Q equals NE, with Q being the total charge, N being the number of electrons or protons or particles or whatever, and E being the elementary charge. So calculate the number of excess charges. I know that the overall charge, according to the problem, was 9.6 times 10 to the negative 19. I'm trying to solve for N because I want to find out the number. And I know my elementary charge is 1.6 times 10 to the negative 19. So if I just divide both sides by 1.6 times 10 to the negative 19, I end up getting, I think the answer is 6. So 6 protons or 6 excess charges, all of those work. Yes, if the product of the factors is negative, the object is attracted. If the product is positive, then they repel. Yeah, that's completely correct. Okay, cool. I'm gonna get started on the lesson now. If we send it to the remind updates on iMessage, you still get the picture of the homework. I'm actually not sure, Gracilis. Try now and let me know. I'm getting a whole bunch of you texting me though, so I won't be able to read through all of them, unfortunately. Not right now. Okay. So let's start with the lesson for today. Lesson for today: gravitational fields. So we've already talked about this in the past. In that puzzle, Miss P said n doesn't have a unit. Yeah, I mean, it doesn't really. N is just number of particles. That's really all it means. It doesn't have like one set unit. It could be protons, electrons, so there's not like one set unit for it. Okay. Steph, I'm about to time you out because I need you focusing on what we're doing, and you're like just going off task. I did not know that. I didn't know what to do for number 4 on the homework mahogany. It's the same formula: Fe equals K Q1 Q2 over R squared. If we didn't do number 6, no, because there was a mistake with number 6, so no stress about that. Okay, so we're gonna get started now. Electric fields. So we've got, when we talk about electric fields, and we've talked about them in the past, we have talked about the idea that we have some field lines, and the field lines are basically describing to you, if I put small positive test charges within my within this field, what would happen to them? So I have this positive charge, and I have small test charges all around this positive charge. And I know that a positive charge interacting with these little invisible, not drawn in positive test charges, they're going to repel. And so I'm going to draw arrows away from positive charges because those small positive test charges would not be attracted to this positive charge in the center. Whereas for something like an electron would attract those small positive test charges, so I have to draw the arrows coming in. Okay, so with that in mind, let's go back. I want to show you now all of the different electric field lines that we've had to do so far. So the first one is when you have a positive charge and a positive charge. So positive and a positive. Like I said, remember that these field lines are always drawn from the perspective of what would happen if I put a small positive test charge around these. No, it's not electrons, dear Lewis. It's small positive test charges. So like a small positive test charge here, a small positive test charge here, a small positive, etc., etc. We always draw the electric field lines based on small positive test charges. So a small positive test charge is going to be repelled by this proton. And so we can see that all these lines are being drawn away from my positive charges. Same idea here. Everything would be repelled here. We're repelling away these test charges. Because again, a positive test charge, the ones that are invisibly drawn all over here, would not be attracted to a positive charge. Now, slightly different. Let's do a negative and a positive charge. Notice again that for all the lines coming away from the positive charge are drawn with arrows pointing away. Because again, those small positive test charges would be repelled from my positive charge in the center. But for my negative side would actually attract all those small positive test charges. So we're going to draw arrows pointing towards the negative charge. Is this note, Stephanie? Yes, I would recommend taking notes on this. You don't have to if you don't want to. No one's going to force you, but if you'd like to, you can. And finally, we have a negative charge and a negative charge. Also, guys, I'm going to put this PowerPoint up on Google Classroom in case you want to like have it. I did send out a worksheet for you to take notes on it, okay? You can't hear me? Is she the only one that can't hear me? I can bring the mic closer to my face too. I don't know if that'll help, but we can try that. Okay. So yeah, so we've got the last case is negative and a negative charge. In a negative and a negative charge, we're going to end up attracting both of these different particles are going to attract my small positive test charges. So when I draw in my lines, I draw lines pointing towards the negatives. Always drawn pointing towards the negatives because again, those small positive test charges, those little invisible charges that I don't actually draw in that are all positive, are going to be attracted to a positive, to a negative charge in the center. Can I turn up my mic? Hold on. I honestly can't, like nothing is different from how this was yesterday. So I don't know what the big struggle is. I don't know if that's helping. Yeah, I guess I'm gonna have to check this out off stream because I have no idea why that's happening. It should be the same as it was yesterday. Yeah, I have no idea. Sorry, people. We'll have to make it work. Okay. Moving forward. Now, this is an image that you have on your worksheet. If you printed it out, if you didn't print it out, then you're going to. Oh, they're playing with me. Awesome, thanks, guys. If you printed it out, then you should have this in front of you. If you don't, you can just draw it in. That's totally fine. And on the worksheet, there's a piece of information that I give you. I give you that you have a mass of the satellite, and the satellite is represented by this little dot right here, this little black dot. I have the mass of Mars, which is a number that I have to give you, and the radius of Mars, which is again a number I have to give you. Now, this other information that I have right here, I don't give to you on the worksheet, but you can pull this straight off of your reference table. Both the mass of the Earth and the radius of the Earth are found on your reference table. That's two different values. So, looking at the images here, we have Mars, and we've got the satellite rotating around Mars, and the satellite is 10,000 meters away from the edge of Mars. For Earth, we have, again, the satellite revolving around the Earth, and it's 10,000 meters away from the edge of the Earth, so we have to keep that information in mind. So, now I ask you, calculate the force of gravity. Now, time out some people, because y'all are not using this correctly. Cool. Awesome. Let's go. We can time out some more. That'd be great. Guys, you're going to see them in a second, okay? Okay, so force of gravity on Mars versus Earth. We can calculate the force of gravity on Mars by doing the following. Well, we've got the formula that we've always used to calculate force of gravity when I give you two different masses. That's going to be G m1 m2 over r squared. G being a constant, we know that the G as a constant exists on our reference table. M1 is the mass of the satellite or the mass of Mars, whichever one you'd prefer. M2 is again the mass of the satellite or the mass on Mars. And r squared is the distance from the center of Mars all the way out. So this is where it gets a little funky. And I'm going to explain how this math kind of works out. So we know that the constant for G is 6.67 e negative 11. Is that 10 to the 22nd or 23rd? For which one? For mass of Mars? It should be 20. I'm pretty sure it should be 23. That's how I did all of my math. So we've got FG, 6.67 e negative 11 times 2 e5 times 6.39 e23 over. Now notice what I'm doing here for the radius at the bottom, because the radius of Mars means from the center point of Mars to the edge of Mars. But that's not where the satellite is. The satellite is not at the edge of Mars. It's going from the center of Mars to the edge of Mars plus 10,000 extra meters. So that's what I'm doing at the bottom for the radius calculation. I don't think I've ever made you do this before, but it's just something I'm trying to expose you to now in case that you are ever asked to do it. Remember that a radius of a planet is only from the center of the planet all the way out. And if we have a satellite farther away from that, or anything rotating farther away from that, we have to add that distance. So again, we have the center of Mars to the edge of Mars, and an additional 10,000 meters. When I calculate that out, I get that Fg is equal to 7.37 times 10 to the 5th newtons. Now, we can do the same thing for calculating the force of gravity on Earth. Fg is equal to G m1 m2 over r squared. Same idea. The only thing I'm changing here is that I am throwing in the numbers for Earth instead of the numbers for Mars. So my radius is going to be different, and my mass is going to be different. And when I solve this out, and again, I'm still doing this plus 10,000 because I'm not just thinking about the center of the Earth to the edge of the Earth. I'm thinking about the center of the Earth to the edge of the Earth plus 10,000 extra meters. And when I calculate that out, I get 1.96 times 10 to the 6 newtons. So obviously, my 1.96 times 10 to the 6 newtons is a lot bigger of a number than 7.35 times 10 to the 5th. And we can talk a little bit about why. So I rewrote my FGs here for both my Mars and Earth. Is this classwork? I saw next to the homework sheet in Google Classroom. Yes, this is classwork. I uploaded it there. So, question, why is the force on Earth greater than the force on Mars? Well, we've talked about this before, the idea of what affects force. Force is affected by mass, force is affected by acceleration. In this case, we know that the Earth has a much bigger mass than Mars. So if you're already taking notes, you can take this notes down. Earth has a greater mass, so it has a greater attractive force than Mars. Simply because, again, more mass means you can have more force. Why is gravity able to attract an object towards a planet even though they are not touching? This is where we start to connect between the idea of gravitational fields and electric fields, because gravity can attract an object toward a planet because a gravitational field exists around the planet that attracts objects. What's that sheet Miss G sent? I'm not sure. What did Miss G send you? How can Miss G send you things? Huh. Oh, I see what she did. You can... I want to say you can ignore that for now. Huh. That is just your homework for tonight. So, what she uploaded. I'm not sure why she uploaded it to this class, but that's fine. It's just the homework that you have for tonight. I was going to upload it later either way, so you're fine. Did I send out the homework? Jose, you can just do that one. The one that she posted. It's the same one that the homework was going to be for tonight anyways. Okay. So I'm going to leave this on the slide for 30 more seconds just to get you, anyone who's writing this down, a chance to write it down. Remember, you're only writing down what has a pencil and is bolded. Yeah. Cool. Alright. I can post the homework now, Jose. That's totally fine. It's literally going to be the exact same thing that Ms. Guerra posted. Okay, I'm going to move on now. So, gravitational fields. Gravitational field lines. There's a big difference between how we draw gravitational field lines and how we drew electric field lines. But the general idea is still the same. We're going to have them point towards the center. And all of these are just gravitational field lines representing the attractive force that Mars can impart on objects around it. So, gravitational fields should only point towards the object, never away. This is because gravity only attracts, it never repels. This is the big difference between gravitational fields and electric fields. Electric fields, we know, can either attract or repel. It depends on if something is a positive charge or a negative charge. With gravity, we know that gravity only ever attracts. So whenever you're drawing in field lines for gravitational fields, you are only ever going to draw arrows that point inward. Now, how can we represent a stronger gravitational field in our drawings? Well, we can just draw in more arrows. So the more arrows you have, the stronger the gravitational field. We know that Earth is bigger, therefore it has a bigger gravitational field. Therefore, we are going to draw in more arrows. How does distance affect the force felt by an object due to a gravitational field? So how do you think spreading out or spacing out a little bit would affect your gravitational force? Well, we know that the farther away that you get, the less you're going to feel something like gravity. So the distance will decrease exponentially. As we increase distance, we will exponentially decrease force felt by the object. And if we think about it, that kind of makes sense just based on our formula that we've been using this entire time, right? This idea that, well, we know that Fg is equal to G m1 m2 over r squared. If I increase this value, it's going to cause an exponential decrease in Fg. Yes, as it passes by, King Cruel, as I don't know who this is. I would love for y'all to use your real names for this. As it passes by, we can use the gravity for some objects to send objects further into space, but that's because there's no force in space in the first place, aside from gravity. Okay. I want to move forward now. Okay. Now, calculating gravitational field strength. So, when we calculated electric field strength, we used this formula, E equals Fe over Q, where E was the electric field strength. I'll go back. Okay. Okay, also, Natalie, remember that if you don't get a chance to write it all down, you'll get a chance to just watch the video again later on. Or you could even just take a screenshot of this right now. I'm going to move forward in like 10 seconds. Okay. So, calculating gravitational field strength. We know that we had E equals Fe over Q as one of the nah, dude. Thanks, you're a god. I appreciate you. So E is equal to electric field strength. Fe is the electrostatic force. Q is the charge. Now, for gravitational field strength calculations, we can do a very, very similar formula. Also, yeah, the units for electric field strength are newtons over coulombs. For gravitational field strength, the formula we're going to use that is on the back of your reference table is that G is equal to Fg over M. G is gravitational field strength, Fg is the force due to gravity, and M is mass. Now, this formula should be looking a little familiar. Also, just the units are newtons per kilogram. The reason why this formula might look a little familiar, and I'm actually going to leave this on here for a little bit so you can get a chance to write it down. But take a look at that formula and think about what that formula kind of reminds you of while I eat some bacon. Okay, I'm going to move forward. So, the formula that should be reminding you a little bit of, this G is Fg over M. If we reformat this and just move M to the other side, if we just multiply by M, we get Fg equals Mg, which is the same thing as Fg equals Mag. So, when you think about it, Ag is the same thing as G. It's the same numerical value. It's the exact same value. Now, we know that acceleration is measured in meters per second squared. G is measured in newtons per kilograms, but they are numerically the same value. A, or acceleration, is the exact same numerical value as gravitational field strength. Exactly the same thing. You don't have to write this down, but it's just an observation that I want to connect back. Also, this is given to you in your reference table. If you check the last page and you check what G is, it literally says that G is acceleration due to gravity or gravitational field strength. Yes, Alex, I'm eating in class. You eat in class all the time. Fight me. Okay, let's do some examples. So, the Hubble telescope orbit is 5.6 times 10 to the 5th meters above Earth's surface. Where is my key for this? Cool. YOLO. I guess we're doing it without the key. So, the Hubble telescope orbit is 5.6 times 10 to the 5th meters above Earth's surface. The telescope has a mass of 1.1 times 10 to the 4th kilograms. Earth exerts a gravitational force of 9.1 times 10 to the 4th newtons on the telescope. The magnitude of Earth's gravitational field strength at this location is. So, you're being asked for gravitational field strength. That's key number one, right? That we're being asked for gravitational field strength. Immediately you should be thinking about G is equal to Fg over M. It also tells you that Earth exerts a gravitational force of 9.1 times 10 to the 4th newtons on the telescope. So we know that we have the value of Fg already. And finally, we know the mass of the telescope is given to us right here. So that's going to go right down here. So the formula we're going to use, G, because that's what we're solving for, is equal to 9.1 times 10 to the 4th. Yeah, yo, what y'all got against bacon? It's delicious. Over 1.1 times 10 to the 4th. And that gives you 8.3 newtons per kilogram. Also, I'm pretty sure we've already solved questions like this before. Like, none of this should be mind-blowing. Instead of calling it Earth's acceleration, we're calling it Earth's gravitational field strength. But same idea. Cool. Moving on to problem number 2. Just kidding. I'm going to leave it up for a little longer, in case y'all are taking notes. Okay. A 2 kilogram mass is located 3 meters above the surface of Earth. What is the magnitude of Earth's gravitational field strength at this location? So, we know that to solve for gravitational field strength, we need to use G equals Fg over M. So here's the problem now. We don't actually have an Fg. So we can solve out for an Fg though. How do we solve out for Fg? We do have a mass. That goes down here. We don't have an Fg. We can solve for Fg using Fg is equal to MAG. In this case, it's going to be 2 times 9.81 to give me 19.62 newtons. This is step number 1. Step number 2 is to now use this formula up here. G is equal to 19.62, the Fg that we just solved for, divided by the mass, which is 2. And here, G, unsurprisingly, is going to be 9.81 newtons per kilogram. Answer choice number 2. Cool, I'm getting a lot of late homework assignments from a lot of you. Damn, it's really gonna suck when you realize you're gonna get zeros for that. More space in your class for some homework. Okay, Natalie, I'll try. Moving on, problem number 3. Oh, Lord. Okay. On a small planet, an astronaut uses a vertical force of 175 newtons to lift an 87.5 kilogram boulder at constant velocity to a height of 0.350 meters above the planet's surface. What is the magnitude of the gravitational field strength on the surface of the planet? So, we are given a force of 175 newtons. Well, first of all, we know gravitational field strength should always be G is equal to Fg over M. We're given a force of 175 newtons. We're told that the boulder is 87.5 kilograms, so that's going to be my mass. The vertical force is my Fg. So this is just going to be G is equal to 175 over 87.5. I think this is 2. Yeah. Which is 2 newtons per kilogram. Cool. Moving on to next question. Which graph represents the relationship between the magnitude of the gravitational force exerted by Earth on a spacecraft and the distance between the center of the spacecraft and the center of Earth? Well, we talked about this already. The idea that this is all based on this formula. F is equal to G, M1, M2 over R squared. What happens to force as distance increases? Well, as distance increases, force is going to decrease exponentially. Natalie, it's not technically review. We are doing gravitational field strength stuff now. It looks like review because remember, gravitational field strength is the same thing as acceleration. Yes, guys, this is all we're learning. Final question. In which diagram do the field lines best represent the gravitational field around Earth? So, this is just keeping in mind that it's the same idea as when we draw electric field lines, the only exception being that we never draw lines away. Because remember, gravity can only attract, it never repels. So, the option here, or the answer here, is number 1. Ooh, sorry guys. Just because number 1 is showing me arrows being pointing towards the center of the Earth, we're attracting through gravity. Alright, that's pretty much it. You have your homework up. Or actually, I'm going to upload it now for period 2. And if you have any questions, you can always text or email. And that's pretty much it. Alright guys, it's good seeing you. Have a good one.